All right, let's go. Number 10, TON 618, the black hole that should not be able to exist. There is a black hole sitting at the center of a distant quasar, approximately 10.4 billion light years from Earth, that has spent decades quietly humiliating every theoretical model physicists built to explain how black holes grow. It is called TON 618, and it is not just large. It is so unfathomably, outrageously massive that astronomers genuinely struggled to accept the measurement when it first came in. TON 618 contains 66 billion times the mass of our Sun, packed into a single point in space. Its event horizon, the boundary beyond which nothing, not even light, can escape, is so wide that it spans a distance larger than our entire solar system several times over. If you replaced our Sun with TON 618, its gravitational boundary would swallow every planet, every asteroid, every comet, and extend far into the space beyond. Neptune's orbit would be deep inside the black hole. You would not even be close to the edge. The problem is not the size. The problem is the age. TON 618 existed when the universe was only a few billion years old, a cosmic infant, and the standard model of black hole growth, where a black hole feeds on surrounding gas and gradually accumulates mass over billions of years, simply cannot produce an object this massive in that amount of time. The physics of accretion, the process by which black holes consume matter, has a speed limit. Radiation pressure from the infalling superheated gas pushes back against gravity, capping the growth rate. Obeying that limit, TON 618 should not exist yet. It needed more time than the universe had given it. Proposed solutions include black holes that were born already enormous from the direct collapse of massive primordial gas clouds in the early universe, or periods of super-Eddington accretion where the growth limit is somehow exceeded. But these remained theoretical patches on a model that TON 618 fundamentally broke. It is the largest black hole we have ever measured, and its very existence tells us that our understanding of how the universe built its most extreme objects is seriously, fundamentally incomplete. Number 9. The first image of a black hole and what it got wrong. On April 10, 2019, humanity saw a black hole for the first time in history. The image, a glowing asymmetric ring of superheated orange plasma surrounding a dark central shadow, was released simultaneously at press conferences on 6 continents. It showed the supermassive black hole at the center of the galaxy Messier 87, a monster containing 6.5 billion solar masses, located 55 million light-years from Earth. The Event Horizon Collaboration, a planet-spanning network of synchronized radio observatories operating together as a single Earth-sized dish, had pulled off one of the most technically audacious feats in the history of science. The image confirmed visually and dramatically that black holes are real physical objects and not merely mathematical abstractions. The shadow's size and shape matched the predictions of general relativity with stunning precision. Albert Einstein's 104-year-old equations, written at a desk with pen and paper, correctly described the geometry of space-time around an object containing 6.5 billion solar masses. The scientific community celebrated. And then, the physicists started looking more carefully. The image showed the bright emission ring was slightly brighter on one side than the other, a signature of the plasma being flung toward us on one side at a significant fraction of the speed of light. The asymmetry matched relativistic predictions, but the exact brightness distribution, the fine structure of the emission ring, and the precise size of the shadow contained subtle tensions with the simplest theoretical models. Follow-up imaging in 2021 and subsequent years revealed that the ring structure wobbles and shifts over time as the chaotic, turbulent plasma surrounding the black hole devolves. The accretion disk is not a stable, smooth structure. It is a violently dynamic, rapidly changing environment that our simulations only partially reproduce. We took the first photograph of a black hole and discovered that the object is even more complex and turbulent than our best theoretical models had prepared us for. Number 8. Cygnus X-1, the black hole that started a bet and ended with a shocking measurement. In 1974, Stephen Hawking made a famous scientific wager with his colleague Kip Thorne. The subject was Cygnus X-1. a powerful X-ray source in our own galaxy that astronomers suspected was a black hole feeding on a companion star. Hawking bet that Cygnus X-1 was not actually a black hole, specifically because he wanted the insurance policy of being right about something if black holes turned out not to exist. Thorne took the other side. In 1990, Hawking conceded. Cygnus X-1 is a black hole. He signed Thorne's copy of Penrose's paper with a thumbprint. That was merely the beginning of the story. For decades, Cygnus X-1 was classified as a stellar mass black hole of roughly 14 to 15 solar masses, consistent with existing models of how massive stars collapse at the end of their lives. Then, in 2021, a team of astronomers published a comprehensive reanalysis of the system using an improved model of its companion star and a precise new measurement of its distance based on radio interferometry. The results completely revised the picture. Cygnus X-1's black hole is not 14 solar masses, it is 21 solar masses. That single revised number broke the existing models of stellar evolution. A black hole of 21 solar masses, formed from a star in our own galaxy at its observed metallicity, the abundance of elements heavier than hydrogen and helium, should not be possible. Stars with higher metallicity lose mass more rapidly through stellar winds as they age, meaning they should not retain enough mass to form such a large black hole when they finally collapse. Cygnus X-1 is sitting right here in the Milky Way, close enough to study in extraordinary detail, and it is more massive than our best stellar physics says it should be allowed to be. The galaxy's most famous black hole quietly revised its own mass and demolished another theoretical boundary in the process. Number 7. GW 150914. The collision that proved Einstein right and created new questions simultaneously. On September 14, 2015, at 5:51 in the morning Eastern Time, two gravitational wave detectors, the twin LIGO observatories in Louisiana and Washington State, simultaneously registered a signal that had traveled 1.3 billion light-years across the universe. The signal lasted a fraction of a second. In that fraction of a second, it recorded the final moments of two black holes, each roughly 30 times the mass of our Sun, spiraling together and merging in a catastrophic collision that released more energy than all the stars in the observable universe combined emit in that same fraction of a second. All of it radiated as pure gravitational waves, ripples in the fabric of space-time itself. This was GW 150914. The first direct detection of gravitational waves, confirming a prediction Einstein had made in 1916 and spent the rest of his life uncertain was physically real. The discovery was monumental, but what it revealed about the black holes involved was immediately puzzling. Both black holes, 35 solar masses and 29 solar masses before the merger, were larger than the maximum mass stellar mass black holes were supposed to reach according to standard models of stellar collapse. Massive stars in the mass range that would produce these black holes are expected, at certain mass thresholds, to be completely obliterated by a process called pair instability supernovae. Explosions so total that the entire star is annihilated and no remnant is left behind. The black holes of GW 150914 were sitting right at the edge of this forbidden mass range. Subsequent gravitational wave detections revealed even more surprising objects, including a merger that produced a black hole of 142 solar masses, squarely in the middle of the mass range that theory said black holes simply cannot occupy. The universe is assembling black holes through mergers in mass ranges that direct stellar collapse cannot produce, and it is doing so at a rate and in configurations that theoretical astrophysics is still scrambling to explain. Number 6. The fastest spinning black hole ever measured, a singularity at the limit of physics. Black holes, according to general relativity, are described entirely by just three properties: their mass, their electric charge, and their spin. In practice, astrophysical black holes are electrically neutral. Any charge is neutralized almost instantly by surrounding plasma. So real black holes have only two meaningful properties: mass and spin. Spin, measured as a dimensionless parameter between 0 and 1, represents how close the black hole's rotation rate is to the theoretical maximum, the point at which the event horizon would rotate at the speed of light. In 2013, astronomers measured the spin of a black hole called NGC 1365 using NASA's New Star X-ray telescope, and the result was extraordinary. NGC 1365's central black hole is spinning at more than 84% of the maximum physically permitted rate. Subsequent measurements of other black holes, including the supermassive black hole in the quasar Markarian 335, pushed the measured spin even higher, approaching 98% of the theoretical maximum. These objects are rotating at rates so extreme that space-time itself is being dragged around with them in a phenomenon called frame dragging, warping the geometry of the universe in their immediate vicinity in ways that have no analogy in everyday physics. The disturbing implication of near maximum spin is what it means for the structure of the black hole itself. Standard Schwarzschild black holes, non-spinning ones, have a single event horizon surrounding a point-like singularity. A maximally spinning Kerr black hole, described by the mathematics of general relativity, develops a ring singularity and theoretically regions of spacetime where causality itself breaks down, where it might be mathematically possible to travel backward in time. Near maximum spin pushes black holes toward a regime where the equations of general relativity begin producing answers that physicists find deeply troubling. The universe appears to be building black holes that approach the edge of what the mathematics can describe without breaking. Number 5. Hawking radiation, the prediction that has never been observed but is destroying black holes right now. In 1974, Stephen Hawking published the theoretical results so unexpected, so counterintuitive, and so deeply unsettling that most physicists initially assumed he had made a mistake. Working at the intersection of quantum mechanics and general relativity, two frameworks that are fundamentally incompatible at the deepest level, Hawking derived that black holes are not perfectly black. They glow, faintly, almost undetectably, but they continuously emit thermal radiation caused by quantum effects at the event horizon, slowly losing mass and energy until, over an almost incomprehensibly long period of time, they evaporate completely. The mechanism is rooted in the quantum vacuum. Empty space is not truly empty. It's seized with pairs of virtual particles constantly flickering in and out of existence, borrowing energy from the vacuum and annihilating each other in fractions of a second. At the event horizon of a black hole, one particle of such a pair can fall inward while the other escapes as real radiation. The black hole loses a tiny quantity of mass to pay the energy debt. Repeated across every point on the event horizon, continuously, this process causes the black hole to very slowly shrink. Hawking radiation has never been directly detected. For black holes of stellar mass or larger, the temperature of the radiation is so fantastically small, millions of times colder than the cosmic microwave background radiation that permeates all of space, that it is completely unobservable with any instrument we could conceivably build. But the theoretical implications are catastrophic for physics. When a black hole finally evaporates, what happens to all the information about the matter that fell into it? Quantum mechanics states as an absolute law that information cannot be destroyed. General relativity, combined with Hawking's derivation, suggests the black hole and everything it ever swallowed simply vanishes. This contradiction, the black hole information paradox, remains one of the deepest, most genuinely unresolved problems in all of theoretical physics. Hawking radiation is a prediction we cannot test, describing a process we cannot observe, sitting at the center of a crisis we cannot resolve. Number 4. The intermediate mass black hole problem, the missing link that refused to be found. For decades, astronomers organized black holes into two neat categories. Stellar mass black holes, ranging from a few to perhaps a few dozen solar masses, formed from the collapse of individual massive stars, and supermassive black holes, ranging from millions to tens of billions of solar masses, sitting at the centers of galaxies. These two populations were separated by an enormous gap, a vast desert of black hole masses in the range of hundreds to hundreds of thousands of solar masses, where almost nothing was found. This was not a trivial gap. It was an existential problem for the theory of how supermassive black holes form. Something has to be the seed. The supermassive black holes at the centers of galaxies had to grow from something smaller. The leading hypothesis was that intermediate mass black holes, the missing link between stellar and supermassive, served as those seeds. But finding them proved extraordinarily difficult for decades, creating a growing suspicion among some researchers that they might not exist in the numbers theory require. Then, in 2020, the gravitational wave event GW190521 was detected, the merger of two black holes producing a remnant of 142 solar masses. The remnant landed squarely in the intermediate mass range. Then, detailed analysis of a dense stellar cluster called B023G078 in the Andromeda Galaxy revealed kinematic signatures consistent with a central black hole of approximately 100,000 solar masses. More candidates followed in other globular clusters. The missing link was not absent, it was hiding, elusive, detectable only through subtle gravitational signatures rather than the brilliant accretion emission that makes supermassive black holes easy to find. But the discovery raised an immediate new question. If intermediate mass black holes exist in globular clusters throughout the universe, why are there so few confirmed examples? And why do the numbers appear far lower than the models of supermassive black hole seed formation required? The missing link turned out to be present, but insufficient, solving one problem while immediately generating another. Number 3. SDSS J1106 plus 1939, the black hole blowing the largest wind in the observable universe. When physicists model the evolution of galaxies, one of the most critical but poorly understood processes is feedback, the mechanism by which the supermassive black hole at a galaxy center regulates and ultimately suppresses star formation throughout the entire galaxy, which can be hundreds of thousands of light years across. The leading theoretical mechanism is the quasar-driven wind, a stream of high-velocity plasma accelerated outward by the intense radiation pressure from the superheated accretion disk around the feeding black hole, blasting through the interstellar medium and sweeping gas and dust out of the galaxy entirely. The theory was elegant. The observational evidence for truly powerful winds was, for a long time, limited. Then, astronomers analyzed the quasar SDSS J1106 plus 1939 using the Very Large Telescope in Chile and measured something that rewrote the scale of what black hole feedback means in practice. The outflow from this quasar is moving at approximately 8,000 kilometers per second, nearly 3% of the speed of light. It carries a kinetic power equivalent to approximately 2 trillion times the total luminosity of our sun, sustained continuously. It is the most energetic quasar outflow ever directly measured, carrying enough power to heat, disrupt, and expel the gas from an entire galaxy on timescales of tens of millions of years. The single black hole at the center of SDSS J1106 plus 1939 is not just feeding. It is actively reshaping and evacuating the galaxy around it, demonstrating with brutal clarity that the supermassive black holes at galactic centers are not passive inhabitants of their hosts. They are the dominant force governing whether their host galaxy lives, grows, or dies. A black hole is controlling the fate of hundreds of billions of stars, and we watched it happen through a spectrograph in the Chilean desert. Number 2. The black hole at the center of our own galaxy, Sagittarius A star, breaks its own rules. For most of the 20th century, the center of the Milky Way was hidden from optical telescopes behind an impenetrable curtain of interstellar dust. Radio and infrared astronomy slowly peeled back that curtain, revealing an extraordinary concentration of mass lurking at the galactic center, a region astronomers designated Sagittarius A star. Decades of painstaking infrared observations at the Keck Observatory and at the European Southern Observatory tracked individual stars orbiting this invisible point source, their trajectories curving through space in tight, high-speed ellipses that could only be explained by a mass of approximately 4 million solar masses confined to a region smaller than our solar system. The conclusion was inescapable. The center of the Milky Way hosts a supermassive black hole. And in 2022, the Event Horizon Telescope collaboration released the first direct image of its shadow, a glowing, turbulent ring of plasma surrounding a dark central region, confirming what the stellar orbits had implied for decades. But Sagittarius A star is deeply strange in ways that go beyond its mere existence. For a supermassive black hole, it is almost completely dormant. The amount of gas and dust falling into Sagittarius A star is roughly 1 million to 1 billion times less than theoretical models predict for a black hole of its mass and environment. It should be blazing. It is barely flickering.
Then, in 2019, it had one of the brightest infrared flares ever recorded, briefly becoming 75 times brighter than its baseline in a matter of hours, for reasons that remain debated. And in 2020, astronomers detected a mysterious structure called the X-shaped radio feature surrounding it, the origin of which is unresolved. A 2022 study also found that the orbits of some of the stars closest to Sagittarius A star show subtle deviations from what pure Newtonian or even simple relativistic gravity predicts, hinting at additional physics operating in the extreme gravitational environment at our galaxy's core. The black hole at the center of our own galaxy is the most studied black hole in history, and it is still actively generating discoveries and contradictions that no one fully understands. Number 1. The black hole that fired a jet across 1.5 million light-years and hit another galaxy. In 2024, astronomers announced the discovery of something that had never been seen before in the history of astrophysics, and that violated every intuitive assumption about how large and how energetic the universe's most violent processes can be. Using the Meerkat radio telescope in South Africa, researchers identified a relativistic jet, a concentrated beam of plasma accelerated to near light speed by the rotational energy of a spinning supermassive black hole that extends continuously for approximately 1.5 million light-years in a single direction. The source is a radio galaxy called Nkatsa, and its jet is not merely the longest ever recorded. It is so long that it has crossed the empty intergalactic void and is physically impacting a completely separate, independent galaxy sitting in its path. The plasma beam from one black hole is ramming into another galaxy at near light speed across a distance roughly 15 times the diameter of the Milky Way. The energy involved is staggering beyond any simple comparison. The jet has been active long enough and is powerful enough to have deposited colossal amounts of energy into the intergalactic medium over millions of years, heating the thin plasma that fills the space between galaxies across an enormous volume. The galaxy being struck has almost certainly had its star formation dramatically altered by the external energy injection. A black hole in one galaxy is actively reshaping the evolution of another galaxy that it has never been gravitationally bound to, separated by 1.5 million light-years of void. This discovery broke the assumed scale of black hole influence. Theorists had long known that powerful radio jets could extend hundreds of thousands of light-years. 1.5 million light-years, terminating in another galaxy, was beyond the range of what existing jet models comfortably predicted. The universe's most powerful engines are not contained within their host galaxies. They are reaching across the intergalactic medium, across distances we associate with a separation between neighbors in a galaxy cluster, and physically altering the structure of the cosmos around them. A single black hole, spinning and feeding, is rewriting the destiny of matter it will never directly touch, across a distance so vast that light itself takes 1.5 million years to cross it. I'll be sharing more similar videos in the future, so subscribe to stay tuned.